Hello Internet, welcome to Fun Project Monday on Tuesday. Yes, we don't care about the day. And it's 4:30 in the morning at my place. Prime time where it matters, prime time wherever you're watching, even a replay. And join me for an hour or two of electronics design, of building a nice product without any kind of project managers, without any deadlines, simply building something, simply designing something. We'll build it up until it's ready designed and bring it to production. I like to enjoy these mornings. I have some coffee, so I feel better. And yes, let's have some fun. And let's see what we did last time. Last time if I have a picture, and I do. we have checked out. I should open the right project, shouldn't I? That's way better. We took a look at the front panel, edited some errors out, and found a suitable connector. The error I found in the aftermath, I said that I wanted to use only 6-pin connectors, and I was quite sure if I couldn't count, because I had a small list prepared with the signals I wanted to use. I couldn't find them. I know, and I now know why. For some reason, I thought of having the for the switch metrics, the signal lines, I thought of having them coming directly from the processor. Well, of course, that's complete bullshit. You don't need that. I would use. I could get them very easily from the because we have so much space left from the latch register, from a register here. So shift register, yes. So that would be would have been very much easier. But yes, we don't care so much about that because it will work so. And now we have some extra pins ready. So if you want to do something on the front panel, which is highly unlikely, we have some pins ready. That's good. Maybe we could add a complete power on-off switch, or having some sort of interface to the front panel. You don't need that. You really don't need that. Okay. So, let's head back to the LED driver. We will pendle back and forth between the different project parts and take a look on this circuit here. That circuit was our power driver for the LEDs. So we have in the middle here we have a controller, a switch mode controller, and this switch mode controller will be switchable between 5 volts and 12 volts with a small circuitry. With a small circuitry in this area, which will allow using any analog strip with a few MOSFETs, or make it a little bit bigger, or to use a small circuit to switch the voltage from the high side to have a possibility of having how do you call it? A digital LED controlled, yes. And yeah, that's everything. So that's one is too much. And now we can start building a little bit on the circuit itself. On the values, required values, we will have the data sheet side by side. So I can, wait a minute, I think I can make this for me a little bit easier. So we can switch between the datasheet back and forth. Oh, that's great. You know, on your OBS you can switch all the can switch everything to the sides. All the control panels, you can switch it out of OBS, and it's way easier to have a control panel directly between the two windows I use. So yeah, let's do this. I can have this up. Now I can do this very fast. That's great. So, okay. Because the datasheet gives us quite some information on how to dimension, or how to estimate the capacitance capacitances we need to use. And yeah, let's start by simplifying the circuits. Because we don't need this. We could use this, but we really don't need this. The circuit with these two resistors, first of all, only these two resistors, is an undervoltage lockout circuit. So the converter itself has an internal undervoltage circuit, which triggers around a few hundred millivolts. But with these two resistors, we can change the threshold of a lockout circuit, and of course that means we can simply leave it away and only use the MOSFET. Can only use the MOSFET to drive the enable pin to turn on and turn off our channel if we don't need it. And because letting it float will result in... Why is my switching stuff is way... Why? That's weird. So, where was I? Yes, we could only use okay, now I'm confused. So we could only use this MOSFET to turn off and turn on the channel, and we could mitigate these two resistors. But we can try to check out what kind of resistor values we will have if we if we wanted to use the circuit. Must have a calculator. And we can start checking out. So what this does is the circuit itself has an internal power source, internal current source, which will pull the pin itself high. So without having anything connected, the circuit will simply work. No problems whatsoever. Adding these two resistors will pull down the current source at some point to an under the threshold, so our device won't work anymore. You only see that are very small current sources, so they're only falling a few microamperes. And let's check it out. Assuming we would use an input voltage of 24 to 20 volts, we could put that in. So 24 volts. Oh, we only want to use 24 watts. We don't want to go into the 50 watts area at all, because that would be causing our voltage range and amps range to be way too high. So we will simply change it, and I will make a quick break. Yes, I will do a quick break. Okay, I'm back. So let's think about this equation again. So what we want to do if we decide for a voltage range, we want to don't stress it too much. So we want to think about having maybe 4 volts of maybe 5 volts or 6 volts of tolerance. So let's say we have a voltage that's input voltage that's specified between 24 and 16 volts. Yeah, that should do the trick. So 24 to 16, 18 volts. 18 volts is much more reasonable. En falling and rising, it would be 1.19 and 1.22. And then we would need to multiply it with the current. That would be IP 0.7. It's 10 to the minus 6. Yes, 10 to the minus 6 times 1 minus Vn, falling, so 1.19 to 2.2, 1.22 plus 1.55. I don't trust this result. Oh yes, we will need to times 10. I don't trust this, like having an... So if you calculate this, I'll come to an 3.5 mega ohm resistor, which seems a little bit too high. I think they have an 3.5 mega ohms. Does this make sense? Times 10 minus 6. Let's check the equation again. 24 times. V start will be the upper voltage bound, if I recall correctly. Yo. 3.5 mega ohms seems way too high. So if we're going to use, if you would to use that, let's put this, let's make that clear in the schematic. Because if we make that clear in the schematic, we can later decide if we wanted to use that divider or not, and later check if we want to use it or not. So let's move that again to the side. Put a box around that. This will be optional. We could also write this correctly. Oh, that's okay actually. No, yeah, it's okay. Write on the voltage together. So, okay. So that would be 3.5 mega ohms, and with the other equation we would come to so let's write it down. start like that. And the other equation would be F4. So let's check the second one, because then we can see if it makes sense. It would be R4 times the end falling, so 1.19. We stop would be 16. No, we said 18 volts minus VEN, 1.19 again, plus R4, so times also EP plus EH, that would be 1.62 microamperes. 1.62 times 10 minus 6. Yeah. 200k, 180k. Well, that makes sense. Or does it really? Yeah, we'll check that. So that's optional. Another thing to consider building this up, because in the long run we want to manufacture it, and if we manufacture it, it would be relatively easy to manufacture it at LCSC or at JSC PCB, because you got the whole LCSC catalog. We already talked about that. So one thing to consider is having all the right resistor values inside, and that's the point where I was a bit not disappointed, but where I got a bit not so happy. DipTrace provides a lot of these. There are quite some lot of these ready-made resistors with the right part number and everything. Fortunately, it's not really enough. Now, how many values do you have here? You have around. You have here. Oh, you have 20 values. That could be enough, but you have quite some. So, if we want to use those, we can use those, but we will certainly need to add some too. So we can think about having, that should be 200k resistor, 180k. So we should certainly start replacing all those placeholders that I put in to quickly populate the schematic with all the part numbers and the appropriate part numbers. Because with that, manufacturing is easier. It certainly takes 3 to 4 hours extra time in the design stage to have all the right parts inside, but it certainly pays off if you want to manufacture a few more. So we'll do this. Let's take a look. As far as I remember, JLC used for manufacturing Uniroyal part series. And we'll take a look on the datasheet for it. Why shouldn't we? And if we go through it, we will get all the part numbers, which we will need to find the right resistor values. So let's see if we find some sort of part designator. Oh no, it's of course in here. So 470 would be 4.7 ohm. And if we go down, we should find all the other values. For example, for that 180k resistor, we want to have a 186. Take a look if we are in the right range. Or 206 if it's inside, and we don't get it. The highest we would get is 124. And that are 2 mega. Okay, now I'm a little bit confused. So we want to have one 200k, yes, that's okay. 0805. 0805 is the, let's say, is the right amount of small enough to handle and or small part and still able to solder by hand. So we'll replace that part with basic parts. And we want to have the 0805 W8F2. It doesn't search that far. So we want to have an 0805 W8F 200. And we want to have a 203. Okay. Should be the right amount. Yeah, that should be about the right amount. And above here we should have an replace. So of course, if I don't have 180 ohm resistor, we would use some kind of why don't I have such area? So basic parts, filter please. Let's see if we get those. Okay. White. Yeah, now we get everything. And we want to have the 335. That should be the right one. That should be, no, that we need one higher. We need the 6. Replace part. 5. Of course, we want to have mega amps, and it seems like it's not. Let's filter. That's the highest we can get. So we use so it would need to use one 1 mega ohm and one 2 mega ohm resistor. Let's stay with 2 mega ohms for first. Yeah, and then we can change it later. No, I don't want to change it later. We will do it now. So we'll add a one higher valued one. Oh, 801. That is an, what kind of that? Oh, 4. First one that should fit too. So replace. So now we have 3 mega ohms, that's great. Okay, now I got my error of the exponents. Okay, good. So, let's put the values beside that to know that we that we didn't took the right values exactly, but that's not a problem. It should be good enough. It could only fry our input circuit if the voltage is too high. So we'll certainly use the other one a bit smaller. We'll calculate that later, but that's good for the first. Let's continue with C2. For C2, we would need to use some. We have some recommended values. We have a table here, and we want to do so much. We don't have C2 recommended. Nope. So we would need to check what they want. C2. Let's check for C2. Let's see. Ah, no, it's C3 in the circuit. Let's check C3. 0.1 mic. So let's check the capacitors, if we get some here. So all the capacitors are from Samsung micro devices. So we should need to check the datasheet to get the right one. Or to get the right... yeah, let's check the datasheet for that first. So we don't search too long for the right values. That would be a little bit too small. But if that's 10, 120, that, yeah, let's check the datasheet. To get the right, let's check the datasheet to get the right, and let's check the datasheet. Don't ask why I use Edge, it's a virtual machine which runs the trace, so I didn't thought about using that. So, with that we should get to the family datasheet, because there isn't a datasheet for one ceramic capacitor, not at that price range. Part numbering. So the first is the size. Size is 2 size go to 10. Or 6 or 3, that's of course not that nice. So I want to have at least 21 in the first digit. When we want to have mostly, yeah, that's not that important, because we will certainly stay in the capacitor range in the temperature and the temperature range. It's not that important. We want to have such hot device. Tolerance codes, part numbering, capacitance, tolerance, nope. Weighted voltage, certainly to keep in mind. Okay, now I completely overlooked the... Oh, here, capacitance expressed in picofarad, those zeros. .06. So for 100 mic, we would need 101, if I'm right. Let's take a look if it makes sense. That could be 100 mic. Yep, that's good. So we replace that one. Basic parts. And we have a CL21. CL21. C101. Yeah. Okay, let's replace that one. And that looks okay. Let's continue with L1. One thing I will add is I will add the component the component values in the view, so that so we can get so we can see what we already done and what we still need to do. So let's check that was the view. Precision. Part markings. And we certainly want to have the values show. Yeah, that's great. So then we will get the right coil. We had some coils in here, I know. Sensors. Oh, I hope so. That would make everything easier. C logic. Inductors. So we certainly search for a 15 mic inductor. Let's see, look. We can read it. That could be 15. No, 15 nanohenry. That's a bit. That's a little bit small. Let's check that one. 100. Yeah, that's simply search. 222. 10, no. 10. 1.4. 1.4. 4.7. 2.2. 1 mic. 68 nanohenry. 50. No, everything is not the right size. Would remove those and search our CES one. For that, I copied the library inside, just to add the right ones later. So for that, I will use certainly this browser, because I have no interest in mucking around with Edge too much. Let's take a look. We want to have a coil, an inductor. Inductors SMD, 150 microhenry. Still 450 over. So let's take a look. Rated current should be 3 amps at least. Let's say 4 amps. So we have quite some still 90 remaining. Ratings, DC resistance, we don't care so much about that. Tolerance, frequency, quality factor. What's the smallest one we can get? 2 smallest packages. 4040, and let's take those with that. So, did we already apply them? That are 15. Let's take the cheapest one. Eaton. the cheapest one with picture. We have some inductors from Vishay. That's B6 amps. Certainly don't need that much. Yeah, we could use these. It has exposed pads, so it could be relatively good to solder, so I'll take this one. So let's add a new part. So what I found here was a library that was that somebody, oh, maybe get here the right one, that somebody copied from the standard part list from, or basic part list from JRC PCB. It was a GitHub repository, and yeah, fortunately the naming is a little bit not that good, but what he did great is the extra sheets here. That's good. So we'll add our inductor here, this BC, however. Put it in the right place. Copy another maybe. Here are inductors, yes. We'll simply copy one of them. I think it would be on the bigger side, so let's simply duplicate that component and add some parts. So we have an so now you're seeing what I do. So we have a BCI HP 1040 SC minus 150 M. The name is the same. Name. Manufacturer is Baocheng Elec. Okay. We don't care so much about the data sheet, if we're honest. But what we care about is that what we really care about is that part number. Let's see, 292, 1232, 1232, 1232, and it's an 10 times 11.6 millimeter inductor. 10 millimeter times 10.6. 11.6 inductor. $29, $21, $232, great. And let's check for the data sheet how the pads are arranged. Okay. BCI HP 1040 SC, yeah, that looks great. And now at the pattern. Let's see what we have in here. So it's 10 times 60. Check for inductors. Inductor chip. Want 10 times 11 millimeters. We have 10 times 20 times 10. No. Let's check that here. That doesn't fit so much, so we'll add a new pattern and get this inside. So let's do a pattern. I hate Windows. Good. So let's say that would be, I call it its Baoqing. Okay. And we will add a new one that would be BCI HP 1040 series. Yeah, 1040 SC. Okay. Have the ref design of L. And now we can add the board outline, or the part outline. That would be A times B, that would be 10 times 11.6. Like that. Okay. So. And B is the longer side. Okay, so I will remove that. So we have B on the longer side. That's easier for me. So. And then we have two pads. Not that complicated. We have two pads. These pads have a dimension of, let's take a look. C will be so the height type dimension. We have a rectangle. The width will be so the height will be 3 millimeters, 4.1 millimeters, 4.1. The width will be B times A, 13.6. So I have the values on the other side. Don't bother to change that. 5.4. So we have 13.2, and we have 8.2. 8.2 divided by 2 is 4.1. I want to have square ones. That's okay. We'll put them more or less side that, so we can solder them later. And if we check the middle dimension, we will get an, how much is that? 7.2, 7.3. That should be 8.2. So we can move them a little bit to the side. To move the same amount to the side. So let's make that a little bit more. Yeah. That didn't help at all. So the problem is with the dimensioning. With the how do you call it? With the grids. But every CAD program I worked so far does this, that you're not really able to have the grids that the parts align themselves to a grid that you don't want to have aligned, but that's good enough. Yeah, that's great. Save. Pattern libraries, no, not components, patterns. And have vouching. Speichern. Great. Now we can simply use it here. Vouching. And can be sure that's the right footprint. Okay. Great. Double check the part number. After we double check the part number, because that's a really important part. That's why we're doing this. To have the part number inside our CAD program. We can save that too. Oh yeah. Copy component to another library. Okay, now why can't I save it? Okay, we do it other way. We will add new library. We'll copy that to another library in, let's say, Uandi. Now we don't need to change that because that has still a reference to the original one. So we'll delete those. Yep, remove that. Still have it saved. So we'll do it in JLC edition. Basic parts JLC extended. Extended, okay. Yes, I want to change that. Let's go to taken, documents, save that, and components. Want to have what I'm currently saving. Yeah, I was saving the right one because I just don't want it to overwrite with my existing ones. It would be not that great. So I want components. I want to have basic parts. Extended JLC. Basic parts JLC extended. And write a capital. It looks nicer. And save that. And bring that up. Save to another library. From here. Nope. Currently, no, I don't want to save that. Move to another library. So, Basic is extended. Okay. Now it's here. Yes. Great. Now it's in. And now we can continue. Now we can continue adding our 50 μ inductor. Replace part. We go to my library and add that one. I don't want this. So, okay. That's ready. Now let's add this 22 mic capacitors, which we already specified after the datasheet, if I remember correctly. And yeah, we should have those certainly inside that library. Let's go to the capacitors. Properties, capacitors, replace part. So basic parts JLC. And we want capacitor ceramic SMD. So we want to have some 20 CL21, 22, 61. So we want to have a 22 free. 22 free should be the right size. CL21, 22 free. Okay. Let's check. That would have been nanofarad. No, that's not enough. It would be 22.6. These parts. Let's get to 22.6. It's even a big one. That's good. And another basic parts. Here we want to have a 22.6 also. Big one, that's great. Now we get to that voltage divider. Voltage divider is of course critical, because here our voltage is actually set, and we will need to change that voltage divider afterwards so it will give us first of all 12 volts and then also 5 volts. Here we'll first give a small capacitor. That one is primarily in there to give some sort of smooth transition, to stabilize the voltage that's actually a little bit to filter the voltage at that point. So we want to have a small one. CL 100, 150, 160. We want to have a 1, yes. 40, no. So let's put in a 33 one. That's okay. That's a bit much. Or what do they recommend? They recommend 75 picofarad, don't we? Let's check again. What are they recommending? 75. That's like a little bit less. But it's so 7 for 1. So I want to take 47 maybe, or maybe 100. 100 is okay. because then the part is also a little bit bigger. That's okay. So C7 will be the same. Yeah, this part number. That will be C7 also. Replace part. Okay. So that's that. You can also put the 222 mics for input filtering. They are recommending one 10 microfarad and one 0.1 microfarad cap. That's okay, that's 0.1, we already have that. We will add that certainly. Okay. Of course, you could do that a little bit faster, but that's not the point here. So we'll put that in, apply filter, and we will add this part also. And for the 22 mics, we'll add a little bit bigger capacitance. Why shouldn't we? Because we are already using those 22 microfarad capacitors, so we can use it here too. Get that part number. And we'll replace that part also. Okay. Because having no electrolytics in your product is, of course, way better. So we have that looks good. So let's go to these resistors. Fortunately, we already got the right values we should use. Oh, and we see if we compared 5 and 12 volts, they recommend for C8, that should be the output. It should be that smoothing capacitor here. No, it's C6. What's C8? They're recommending a C8 that doesn't exist. It certainly should be C6, shouldn't it be? Interesting. That would certainly be C6. So R2. R2 would be the lower one, if I'm not mistaken. No, that's the middle one. R2. So we'll give it to them. It should be 200. So I want to have an 0805. 003. What? W8 F003. That should be our 100. Should be our 100k resistor. Yep. Then up here a 50 ohm resistor. Do you have another 50 ohm? No, we don't. Replace part 50 ohms. Filter have 50 0. Oh, come on. Okay, yeah, 490. Ah, Even not. 4911. No, that's not the right one. That's way too high. Place part. 4701. Let's see what's available. We have 51. Yeah, we have 0805. That's okay. But don't have 50s? Don't want that. Okay. Okay, that's of course. We will change that. Why do I have a pattern editor? I don't have a pattern editor. Let's take a look. Attached pattern. So let's replace it again. $51 ohm. No problem. Oh yeah, we'll remove that one. Certainly don't need that. And for the 12 volts, we want to have an. For the 12 volts, we want to have R3 is 4.32. We'll first use the 13.6 attached pattern. So, properties replace part. So we want to have an 13. Apply filter. That could be, actually could be directly the right value. It is 13K, and now that's for 5 volts. And now we will need to calculate R6. So when we have R6 on, we will have 13K. No, we need to calculate R6. So if we have 13K and R6 in parallel, we get 5.23 5.23K at the output. Because we need to change the voltage, and this divider here is a feedback loop for the controller, so we need to change that. So for that, we will go to the tablet and simply calculate it through and see if I can manage that on live stream. So let's take a look. Of course, if we have our voltage divider, we don't care so much about the divider. So the actual circuit looks something like that. So that we have our, let's change that a little bit. That's way more. That's way better. So of course, our actual circuit would look like this. That we have our two. This is one we can turn on and off one, and that goes back as feedback. Because R7 here is only limiting the current flowing through Q7 while it's turning on. So we'll simply take the we'll simply put in the R100K resistor. That's good enough. We already have that in the circuit. Yeah, that's okay. Good. 100k. So that's all that. That should be everything. And that are 15. Certainly 15 microhenry. Yeah, we populated all the voltages. That should be what that should work. That should work. And now we'll add 3 more. Oh yeah, we certainly need to add another thing. We would need to add some resistors for these MOSFETs. So we'll disconnect all of those. Delete from that. So fortunately these nets still exist, but we now delete. But certainly only nothing's connected. So we'll delete all of these nets. So, and now I'm thinking on doing another cost-saving attempt. Of course, we don't have any project managers, no real cost problems, but certainly I don't want to waste, drain so much of my own money. So I will. We want to check if it's viable to use a resistor network instead of an resistor network instead of separate resistors. We should get in DipTrace. DipTrace already suggests us to use or already has some 100k resistor networks. Let's see. No, that's 10k resistor network. We'll see if we get 100k resistor network, because with a 100k resistor network we can eliminate this resistor, we can eliminate this resistor, and we can use another one. So we can eliminate these 2 resistors, because 200k resistors equal to one 100k resistor, and we can certainly use it for here. So a lot of positive upsides. And let's see what LCSC is offering us. If we stay in the same series. So let's check for that. 4D0 to WG to WG J103 TC. Okay, it's not available. G. Okay, let's use only this and see how big it is. Oh, they are quite small parts. 0402. I certainly don't want to solder those. No way. Or maybe we can get but certainly we can get bigger arrays. Let's give us a resistor network of 100k. And 0603 times 3. So it's still bigger, but it should be having. But we should be having multiple. Oh, I like Chinese data sheets. Let's take a look. So it should have a size plus should multiple sizes besides that, or it is that size and has smaller contacts, in which I wouldn't use those because I didn't put them in the design until now. But for some reason I don't see the right. Here. So the one we have a 4D 03. So the whole length of a part are 320 and 4D 03 here are 320 millimeters. 320, 120, 6, okay. So certainly multiple small resistors, yes, put or collude together. Maybe a little bit bigger one. But having 06 of these in that kind of package should be pretty sortable too. So we will use that one. And non-K resistors would make price-wise, we can compare the prices. So one resistor network would cost about a cent. Oh, but we need to buy. Oh no. We do need to buy 50 because we are. No, not an option. You would need to buy 50 of those. And that's the point. It doesn't. That's no real use to use those. So we will simply stay. I'll simply stay with the normal ones and get us some copies. Why not? So we will have a lot of fun soldering resistors in the first prototype. Good. Let's put all of us in. So these resistors, this resistor, and that resistor. We'll connect them to the net, add to net. Oh, please don't. No, 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 please not. We destroyed the nets. Shit. I didn't want to say that. So, channel 1. Enable voltage. I will change the name a little bit to have enable V. Yeah, channel 1 enable voltage. That's okay. NV. Then we have channel 1 change voltage. Add to net plus channel 1. CHGB. Okay. Then here we have add to net. No, wait a minute. Change mode. That's not change mode, that's channel 1 change mode. Channel 1. Connection manager. Nope. Plus channel 1 change mode. Okay. Can change the mode. Then we have here channel 1 change voltage. Channel 1 change voltage. And here we have red, green, blue again. Make it look a little bit nicer. Okay. Channel 1 blue. Channel 1 red. And Ethernet. Channel 1 green. And it's called green. So, okay. So that should be it. That certainly should be it. Yeah, that's all the power circuitry. Of all the values, all the right components for pick and place. Yeah, or component designators for pick and place. Yeah, you can be happy. Great. That should be enough for today. Goodbye, Internet.